All right, you guys ready? Number 1, Chris. Number 1, the coefficient of x squared in this expression is -15. Very nice. Number 2. Is anyone? Oh, I'm just kidding. I have the spinning wheel of doom. Adam.
2 to 5.
Yes. 2 to 5 can be written like this, or you can write it 2 to 5 like that. Oh, yeah, sure. 2 to 5. Didn't want to overwhelm you, but that's awesome. 2 to 5. We got 3 different ways. All right, Alec, number 3.
2 terms.
Yeah, 2 terms. Dos, for those Spanish speakers out there. Number 4, Andy. Alrighty. We will pick someone else. Lexi. Yes, ma'am. 180. For number 5, Jared. Yep, he's here. Number 5. That's not what I got. 2.3. I think that would be right. In fraction form, it would be 143 over 60. Hopefully that's what people have. And I think if you were to do that division, you would get 2 point something. Lastly, for number 6, Nathan. I definitely saw him. Oh, okay, that weirded me out for a second. All right, Jenna. 6. Very nice. 56. All right, last 3. These are a little bit longer. Ryan. Squared, yeah, for those 2 middle ones. Yeah. So x cubed plus 3x squared y plus 3xy squared plus y cubed is what you should have gotten. You would have FOILed and then you would have had to distribute. It was a whole thing. Wow, Alec, it keeps... Noah. Oh. That's okay. Alrighty. That's okay. Gio, do you have number 8 done?
Yes. 25x cubed
Mm-hmm.
plus 25x squared plus 15.
So the only thing that was off was the x squared term. It was 75. So it's 125x cubed plus 75x squared plus 15x plus 1. Last one, Emily. Okay, that's okay. Riley. Yes, all of that, yes. Very good. Last period when someone ranted off that answer and got it all right, we had like an applause session for them. It was great. There you go. She deserves it. -8 y cubed. Alrighty, are we good with those? Good with our warm-up? If we are, we shall proceed. Alrighty, we're going to make a tree diagram. We're using a tree diagram to determine the number of ways to rearrange the letters in the word math. So, let's begin. We have 4 events happening here. We have to pick the first letter, then the second, then the third, then the fourth, right? If we're rearranging them and trying to figure out how many ways that can happen. So, to make it easy, let's start with the letter M. Say the first letter we pick is M. What are our options for the second letter? Yeah, Noah? Yeah, we can pick either A, T, or H. Those are our three options after we picked our first letter as M. If we did pick A, our two options after that would be T or H, right? If we picked M-A-T, what do we have to pick then? H. That's the only thing that's left. M-A-H, we'd have to pick T. That's what we're doing here. We're creating all these different scenarios to count them up to see how many different ways we could rearrange the letters. So if we picked M and then T, we could pick A next, or we could pick H next. If we picked M and then we picked H, we could pick A, or we could pick T. And then the last letters would be just the only thing that you didn't pick yet, right? Because we're not repeating or anything. So we could pick T here and A here. How many ways is that? How many different arrangements? 6. That's 6 different ways. He's seeing that this is one pathway, then 2, 3, 4, 5, and 6. That's 6 ways. Well, all we did was start with the letter M, so we would have to start with the letter A, and start with the letter T, and start with the letter H too, and do the same thing in branches, and figure out how many ways. Well, how many ways would there be if we started with A? 6. And for T and H as well, 6. So that's kind of like a really, really long way to figure out how many different arrangements there are, when really there's this really nice principle we have called the fundamental counting principle that we can use in these situations where we have these events occurring. In that case, it was 4 events. We had to pick the first letter, the second letter, the third letter, and the fourth letter. So in a situation where there's only 2 events occurring, we would multiply how one event occurs in M ways, let's say, and how the second event occurs in N ways together. So that's how many ways they could occur together. So that would be M times N ways that 2 events can occur. If one event can occur in M ways and another event can occur in N ways, then the number of ways that they can both occur is M times N. For 3 or more events, it works the same way. You're just multiplying together the ways in which each individual event can occur. You're multiplying them all together. So they said, for example, if we're talking about 3 events occurring in M, N, and P ways, the number of ways that all 3 would occur is just M times N times P. That's the number of ways all 3 of the events can occur. Are we okay with this? Because we're going to work with some examples using the principle. It's exciting. There's pizza involved, I know. Don't go crazy. We're going to talk about all these different options for pizza. There's a lot of pizzas happening. Hold on to your desks. You have a choice of 3 crusts, 4 cheeses, 5 meat toppings, and 8 vegetable toppings. And they want to know how many different pizzas we can create with one of each of those. So we would use our counting principle to find the total number of pizzas. So we would multiply the crusts. That's how many. Cheeses, 4. Meats, 5. And vegetables, 8. We have to take all of those events into account. So our first event, choosing the crust, there's 3 ways that can go down. Then we have 4 ways for the cheeses, 5 for the meats, and lastly 8 for the vegetables. How many different pizzas can we have? 480 pizzas. That is a lot of pizzas. You could eat them for days and days and days. Are we okay with how we use the principle there? It's just multiplication. Sometimes that's a really good way to think of this fundamental counting principle. It's multiplication, right? All right, this is your little bit of independent practice here. It's related back to that first example we did with the word math. now that we know this counting principle, well, let's use that to determine the number of ways to rearrange the letters in math. So think about the different events that are happening here. Remember I said there's an event, there's a first event that we have to deal with, then there's a second, then there's a third, and then there's a fourth. Does anyone know what those events are that I'm talking about in this situation? Yeah. Yeah, you're picking, so we have to pick the letters as we go. So the first event is picking the first letter. Then the second event would be picking the second letter. The third event would be picking the third letter. And the fourth event would be picking that fourth letter. So I want you to kind of work with this and see if you can come up with the right answer here. Think about the options we have. Good. For the first event. Nice. And then for the second event. Nice. That is not correct. So think about, not quite. This, I mean, that's the right answer, but think about how many options do we have for this first spot? 4. We have 4 options. We can pick M, we can pick A, we can pick T, or H. We have 4 different options. Okay, well, after we pick A, let's say. What if we picked A? Then what do we have left? How many options? 3. We just have 3 options left. Then we have only 2 letters left to pick from. And lastly, just that one letter that we have to go with. So I picked A for this one. We had to pick from these 3 left. H, say I pick. T, well then I have to pick M. That's my only option. I have 1 left. What does this equal to? 24. Does that line up with our tree? Where's our tree diagram? There it is. 6 plus 6 plus 6 plus 6. What's that? That's 24. You just verified that the fundamental counting principle is legit. You calculated how many ways we could rearrange the letters in math. Are we okay with this? Why these are separate events that are occurring? We're picking the first, we're picking the second letter, the third, and the fourth. Yeah? Alrighty. Moving on. We're going to use that idea, the fundamental counting principle, but now we're using it with repetition. With the word math, we used each letter once, right? We only used each letter, we did not repeat. Here, we're going to have situations where we have to think about our options in each of those events. So, Pennsylvania license plate. It is true that we have 3 letters and then 4 digits, right? You've seen license plates. So, we have to kind of lay this out in different events, and I personally like to look at it like these little dashes, like this is my first event, my second, my third. We're going to have 7 total events happening here, right? We have 3 letters to fill, and then 4 digits. So my first event is a letter, and then we have a digit, a digit, a digit, and a digit. They're asking us how many different license plates are possible in Pennsylvania if we are allowed to repeat letters throughout one license plate. So think about this for a second. How many options do we have for this first letter spot? 26. How many letters do we have for 26Y? Because we can repeat, so we can pick the same letter twice. And then the third one is also going to be 26 again, right? Digits, how many options do we have there? 10, 0 through 9, right? That's 10 digits. And we can repeat, so each time we have 10 to pick from. We don't have to eliminate or anything because we're allowed to repeat. So, how many license plates? Yes, sir. Yes. Yes, that is correct. That is a lot of license plates. That is a lot of license plates. Now, they want us to think about how many different license plates are possible if letters and digits cannot be repeated. So I want you to take a moment and maybe set it up the way I set it up. Write it out like that. I'll give everyone a second to set that up. We're trying to set up that B. I think it would help if you turned forward. You just are so excited to answer this question. All right, so I'm going to ask a couple different questions so that you eager beavers can all get to answer. Gio, can you tell me what numbers go in these slots? You are exactly correct. Noah, can you tell me why these numbers are what go here? Right. So here we picked from 26 letters, but then we picked a letter, so we had to take that one out of the bunch. Now we only have 25 to pick from, and 24. And then we had 10 digits to start out with, and then 9, and then 8, and then 7. Do we have questions about that? Jenna, are you okay? Go ahead. That's still a lot of license plates either way. It's a lot of license plates. Are we okay with this fundamental counting principle, yeah? Alrighty. Moving on to some lovely definitions here. Permutations. Does anyone recognize that word at all? Is it a weird word? All right. Fine, we will define that word for you. An ordering of objects. An ordering of objects. Yep, that's all it is. An ordering of objects is a permutation. Think of maybe like a locker combination. Usually it's like 3 numbers. Well, if you try and dial in those numbers in the wrong order, it's not going to work. You need them in the right order. And that's how I think of permutations. It's like a locker combination. You need to have 7, 13, and 12 in that order. It won't open if you do it in a different order. So that's what I think of when I think of permutations. Factorial. Get excited. Exclamation. N factorial. That's how you say this. N factorial. And it is defined as n times n minus 1 times n minus 2 times all the way down to 1. All the way down. So if we're doing 100 factorial, we have to do 100 times 99 times 98 times 97. All the way down to 1. The keystrokes in your calculator for this, you go to math, then you scooch on over to prob, and it is option number 4. So we'll jump over there and go ahead and do some of that. So why don't we do 10 factorial? You can do, whoa, that's not what I want. 10 factorial, that's what it should look like. That's when you take 10 times 9 times 8 times 7 times 6. That's what your calculator is doing all the way down to 1. And that's the number you get. Yeah, type in the number first and then type in factorial. You can test it out with any numbers you would like. question. What do you think this is going to be? Yeah? And did you try that out? Or you just know that fact? He is correct. 0 factorial is 1. And the reason why is, so factorials are kind of just like arrangements. And so we're thinking about 10 things being arranged. Well, 0 things can be arranged in just one way, because there's nothing to do with it, right? And it's kind of weird because, well, 1 factorial is also 1, but if you think about it, 1 thing can be arranged in one way, so it makes sense. And 2 factorial is what? What's 2 factorial equal? 2, because 2 things can be either arranged this way or this way. So if you think about it as an arrangement of things, well, 0 things can be arranged in just one way. Good question. All right, we are pros at factorials. Let us move on to this idea of permutations of n objects taken r at a time. N objects taken r at a time. So the important part about this, you get this notation here. It's written like this, with a little n and a little r next to the big P. The big P obviously is representing the word permutations. N and r, as you can see, n and r, they kind of define it in that sense. N is a distinct number of objects, and r is a certain number of those whole objects taken from that group. So I've used this example before. Say we take 5 sticky notes. That's our total. That's our n, 5 sticky notes. And I want to know how many ways we can rearrange 3 of them. So my r is 3. I want to know how many ways that I can rearrange just 3 out of the 5 objects. So that's a situation where you have this whole and you're just using part of it as what you want to rearrange. So the way we define this, the formula, is n factorial over n minus r factorial. N, we said, is the distinct objects that are in this situation that we're talking about. There could be 20 boys, that's what we're talking about, or there's 30 people in the class, that's the distinct objects. R is the arrangement or ordering that we're asking for. Arrangement or ordering, whichever you prefer. But the reason that this is helpful is looking at the R's, sometimes it's helpful to remember, oh, I want the arrangement of 3 of them, or of 5 of them. And so the R's sometimes trigger that memory. What does R mean again? So, the question I have for you, do you think R can be bigger than N? Why not? Right, you're right. R will never be bigger than N. R is being taken from N. Can R equal N? Yeah, it can. R can be the same as N. What if we want 10 people in 10 places? So we want to see how many different ways we can rearrange them in those 10 spots. That's 10 objects in 10 different spots. So N and R can be the same number, but R can never be bigger than N. N is the whole group of whatever object we're working with. So the keystrokes to utilize this on your calculator would be math again, and probability again, and number 2. So for that, I'd like you to jump over. I'll just use my sticky note example. 5 sticky notes. Sometimes you have to type that N in first. Some newer calculators you can type it in after. But 5 next to the N, and then 3 arrangements, there's 60 different ways to arrange 3 out of 5 sticky notes. That's wild. If we do want to check, so I said, whoop. Alrighty. So if I had those 10 spots and I had 10 people to fill those spots, how many different ways could we arrange them? Holy cow, big number. Wait, do we recognize that number? That kind of 10 factorial. Yeah, huh. We'll have to think about that. Keep that in mind. All right, we're okay with this idea of permutations of n objects taken r at a time? We're okay with that? I think we're going to do a good example that'll help us see how it all plays out. So 8 teams are competing in a baseball playoff. They want to know how many different ways can the baseball teams finish in the competition. So the best thing to do here would be to figure out, obviously, what is n and what is r first. So let's think about this. We have 8 teams, and we want to know how many different ways these teams can finish in the competition. Does anyone have any ideas about what n could be? Megan, yeah? N is 8. There's 8 total teams. That's how many distinct objects there are. Does anyone have any ideas about r? Go ahead. It's also 8. There's 8 different spots. First place, second place, third place, fourth place, all the way up to 8th place. 8 different spots that we can be rearranging these objects in. So that looks something like this. 8 for our n and 8 for our r. On your homework tonight, you're going to have permutations like this, and instead of just plugging them into your calculator, I do ask you that you utilize your knowledge of the formula and actually write them into the formula before you just plug them into your calculator. I think it helps with remembering the formula and just processing what's happening and what your calculator is doing. So we're rearranging 8 teams in 8 different ways. So, well, what's on the bottom there? What does that end up being? 1, because it's 0 factorial, right? We discovered that 0 factorial is 1. So, do you remember what Luke just said? That when we take n and r as the same number, we're just taking that factorial? Well, look what just happened. That's exactly what he said. If we have n and r as the same, we're just taking n factorial. And does someone have that answer for me? Yeah, Alec. 40,000. That sounds right. 40,320 ways? You are correct. Very nice. All right, let's see if we can work through this one. In how many different ways can 3 of the baseball teams finish in first, second, and third? So what is our n here? I hear a couple different things. I hear 3 and I hear 8. 8 is the total, and that is n. There are 8 different objects we have to pick from. R is 3 because we want to rearrange in 3 different spots. So we have first place, second place, and third place, and we're picking from 8 different teams who goes in first, who goes in second, and who goes in third. Kind of picking all the different possibilities that could occur there. So in this case, we have 8 factorial over, what does the bottom look like? 8 minus 3, I heard that. Thank you. 8 minus 3 factorial. So we're left with 8 factorial over 5 factorial. If I see that you understand what the formula is and how it works out, you don't have to sit there and calculate 8 factorial and 5 factorial. You could either plug in 8 factorial divided by 5 factorial, or you could just plug in this this permutation there. But I do at least want to see that you're utilizing the formula on the homework. So just wanted to clarify that. And do we have an answer for this one? Yeah. 336 ways. If you think about it, that kind of makes sense. Well, we have a lot less options for only 3 spots. We have a lot of options if we have 8 teams filling 8 spots. It's a lot of different ways that can turn out. But with only 3 spots, only so many things can happen in those spots. Is that clear? We're okay with that? All right. We'll leave that for tomorrow. What I would like you to do for the rest of class is maybe pull out your homework for me. Do you have your books? No? All right, so my idea here